This research paper presents a novel approach to enhance content caching efficiency in wireless networks by integrating recommendation mechanisms. The authors model the caching with recommendations as a combinatorial multi-armed bandit (CMAB) problem, aiming to maximize cache hits over time. Each content corresponds to an arm in CMAB, and the objective is to decide which contents to cache and recommend simultaneously to optimize caching performance. The paper begins with a review of related works, highlighting the benefits of integrating content recommendations in caching strategies. It then presents a system model for content caching with recommendations, formulating the problem as a CMAB. The authors propose a UCB-based algorithm to solve this problem and provide an upper bound on the regret of their algorithm. The performance of the proposed algorithm is evaluated numerically and compared to existing algorithms in the field. The paper concludes with insights into future directions for this research area, emphasizing the potential of combining caching and recommendation strategies to improve network efficiency and user satisfaction. The key contributions of this work include the development of a new approach to enhance caching efficiency through joint optimization of content caching and recommendation, and the formulation of the problem as a CMAB. The proposed algorithm and its performance evaluation offer valuable insights for researchers and practitioners working on optimizing content delivery networks. In mobile edge computing systems, effective content caching is crucial to maximize cache hit performance. To address this challenge, a recommendation strategy can be employed. The relationship between recommendations and user preferences is critical, as users' access patterns often exhibit spatio-temporal correlations. Understanding these correlations can significantly improve the cache hit rate. Content caching aims to reduce latency and improve the overall user experience by storing frequently accessed content at edge nodes. The cache hit performance can be measured by the cache hit rate, which represents the ratio of successful cache requests to total requests. Maximizing cache hit performance is essential for reducing network congestion, latency, and server load. The proposed recommendation strategy is based on a probabilistic approach that captures users' spatio-temporal behavior. This approach leverages the Markov chain Monte Carlo (MCMC) method to estimate users' content access probabilities. The MCMC algorithm samples user preferences and computes the conditional probability of content requests based on spatial and temporal contexts. To evaluate the proposed strategy, the authors developed a cache simulation model that mimics the behavior of edge nodes. The model integrates user preferences, content characteristics, and caching policies. Experimental results show that the proposed recommendation strategy outperforms existing caching methods in terms of cache hit rate, especially under dynamic user mobility scenarios. However, this approach assumes a known probability distribution of user preferences and may not perform well with unpredictable or changing user behavior. Future work may involve integrating additional context information, such as network conditions and device characteristics, to improve the robustness and adaptability of the proposed recommendation strategy. In this section, we introduce an upper confidence bound, UCB-based algorithm, Algorithm 1, to solve problem 4. This problem involves maximizing the expected number of requests for cached contents while considering the impact of recommendations on user preferences. The UCB algorithm is a well-known strategy in multi-armed bandit problems, which are used to balance exploration and exploitation in decision-making processes. Algorithm 1 utilizes the UCB strategy to select the most promising content to cache and recommend to users. It does this by maintaining an estimate of the expected number of requests for each content, along with a confidence interval around this estimate. The algorithm then chooses the content with the highest upper confidence bound, ensuring that both exploration and exploitation are balanced effectively. The key steps of Algorithm 1 include initializing the estimates and confidence intervals for each content, selecting the content with the highest UCB, updating the estimates and confidence intervals based on user requests, and repeating these steps until a stopping criterion is met. This process allows the algorithm to adapt to changing user preferences and content popularity over time. The performance of Algorithm 1 is evaluated through theoretical analysis and simulation experiments. The results show that the proposed algorithm significantly outperforms baseline strategies in terms of maximizing the expected number of requests for cached contents. This demonstrates the effectiveness of the UCB-based approach in solving problem 4, and highlights its potential applications in real-world content caching and recommendation systems. The proposed algorithm's performance is evaluated for both uniform and XIV distributions. A crucial aspect of the algorithm is that it only recommends cached contents, which may not align with user preferences. This limitation could lead to suboptimal performance in certain scenarios. To address this, the algorithm utilizes a probabilistic caching strategy based on content popularity and user request patterns. This approach aims to minimize the probability of cache misses while maximizing the hit rate. In the uniform distribution scenario, the algorithm demonstrates a high hit rate, indicating efficient caching and recommendation of popular contents. However, under the XIV distribution, where content popularity follows a power law distribution, the algorithm's performance degrades slightly due to the increased variability in content requests. The evaluation also highlights the importance of considering both content popularity and user preferences when designing caching strategies. The algorithm's reliance on cached contents may limit its ability to adapt to changing user preferences or new content additions. Future work includes exploring adaptive caching strategies that can dynamically adjust to shifts in user demand and content popularity. Additionally, integrating machine learning models to predict user preferences and adjust the caching strategy accordingly could further improve the algorithm's performance. In conclusion, the proposed algorithm shows promising results in terms of hit rate and efficiency, particularly under uniform distribution. However, its limitations under XIV distribution and potential lack of adaptability to changing user preferences underscore the need for continued research into more dynamic and adaptive caching strategies. The performance evaluation of the proposed UCB-based algorithm for content recommendation in a caching system is the primary focus of this section. A comparative analysis with the standard CMAB UCB algorithm, the greedy algorithm, and the epsilon greedy algorithm is conducted. The experimental setup includes a total number of contents n equals 50, cache capacity c equals 20, and the number of users u equals 20, with eta equals 4. To derive an upper bound for the regret of their algorithm, the authors utilize Hofding's inequalities to bound the probabilities of certain events. They then define L, K as a function of T, alpha, and delta E, K, and present two lemmas that provide upper bounds for the expected values of text given specific conditions on Nk, T1. These lemmas are used to obtain the regret bound in Theorem 1, which is the main result of this section. Numerical results comparing the performance of the proposed algorithm with other algorithms under various system parameters are also presented. The figures provided in the paper show the performance of the proposed algorithm for different values of WREC and alpha, as well as a comparison with other algorithms. The findings suggest that the proposed UCB-based algorithm outperforms the standard CMAB UCB, greedy, and epsilon greedy algorithms in terms of regret, demonstrating its effectiveness in content recommendation and caching. The results emphasize the importance of considering the impact of caching on content recommendation and the benefits of using an adaptive exploration strategy. The research paper presents an experimental evaluation of a novel UCB-based algorithm for content caching with recommendations, formulated as a contextual multi-armed bandit problem. The algorithm's performance is compared to existing algorithms, including the E-greedy algorithm and the CMAB UCB algorithm. In the first experiment, the proposed algorithm outperforms other algorithms, with a uniform distribution over recommended contents, WREC_U set to 0.95 for all users, alpha equal to 5, and E equal to 0.4. The results demonstrate the algorithm's superior performance. The second experiment evaluates the algorithm's performance with varying WREC_U values, revealing that regret decreases as WREC_U approaches 1. This is expected, as users tend to accept recommendations more frequently when WREC_U is high. The third experiment examines the algorithm's performance with different alpha values, showing that regret remains relatively invariant to changes in alpha. In the fourth experiment, the algorithm's performance is evaluated using a ZIF distribution over recommended contents, instead of a uniform distribution. The results indicate that the algorithm's performance is similar in both cases, supporting the notion that the position of recommended content does not affect its request probability. The paper contributes to the field by analyzing the content caching problem with recommendations, proposing a UCB-based algorithm, and comparing it to existing algorithms. Future work includes exploring alternative recommendation models, incorporating recommendation quality, and considering unknown WREC_U values. The appendix presents the detailed proofs for two crucial lemmas, Lemma 1 and Lemma 3, which are essential components of the research paper. The proof of Lemma 1 commences with the equation R, T, equals Tx, where Ux and Iprec are defined. The equation is then expanded and simplified using the definitions of x** operator UI and x, t, UI, which are indicator variables representing whether item I is recommended and belongs to set Y or Y, T, respectively. This simplification process leads to the expression Txi element of EPTXT equals 1xi element of Y, T, P, which forms the foundation for further analysis. On the other hand, the proof of Lemma 3 involves bounding the expression in equation 21. This bound is derived by applying the max operator over possible values of y, 1, y, 2, y, t. The bound is then rewritten in terms of increment e, k, which represents the maximum value of increment e, k over e element of y. The values of increment e, k are ordered in descending order, and the set y is redefined as y equals a for all I element of 1, 2, c. The right-hand side of equation 24 is then rewritten in terms of ne, k, which represents the number of times content k is selected under certain conditions. In summary, the proofs presented in the appendix provide a detailed and technical explanation of the mathematical manipulations and equations used in the research paper. These lemmas form the basis for understanding the underlying principles and methodologies employed in the study, maintaining the logical flow and ensuring the accuracy of the findings. In the context of a learning algorithm, the authors derive a bound for the expectation of the sum of errors. They initiate this process by presenting a set of inequalities that describe the relationship between errors and the number of samples. Specifically, they demonstrate that the sum of errors is bounded by a function of the maximum error and the number of samples. The authors then utilize a lemma from a previous work to obtain a tighter bound on the sum of errors. This lemma states that for a sequence of positive numbers, the sum of the numbers divided by their squares is bounded by twice the largest number in the sequence. Applying this lemma, the authors obtain a bound on the expectation of the sum of errors, which is a function of the maximum error, the number of samples, and other parameters of the learning algorithm. Next, the authors provide a proof for lemma 2, which involves bounding the second term in the lemma. They employ the law of total probability to decompose the term into two events and then bound each event separately. The first event is bounded using the assumption that the error decreases exponentially with the number of samples, while the second event is bounded using the assumption that the number of samples is large. The authors then take the expectation of the bound and simplify it using assumptions on the parameters of the learning algorithm. They finally obtain a bound on the expectation of the sum of errors, which is a function of the maximum error, the number of samples, and other parameters. This derivation presents a technical bound on the sum of errors in a learning algorithm, leveraging mathematical inequalities and probabilistic arguments. The result is a key component of the learning algorithm's analysis and provides insights into its performance.